Hi, I'm Bob. Welcome back to 5-Minute Econometrics. In the previous topic, we discussed the properties of the OLS estimator when the outcome variable is mismeasured with error. Today, we will explore a more important problem about the measurement error. That is, when the explanatory variable is subject to measurement error. We start with a model with one explanatory variable. Suppose the true relationship model is as follows. The x1 star is the true value of the explanatory variable. It is mismeasured with error. The measurement error, E1, equals x1 minus x1 star, where x1 is the observed variable. We plug the expression for x1 star into the true model to obtain the estimated model. It is the model we have data on and estimate. If the measurement error in the explanatory variable, E1, is not correlated with the observed explanatory variable, x1, then the OLS estimate beta 1 hat is unbiased and consistent. But this is not the case we are usually concerned about. What we usually discuss in econometric analysis is the case where the measurement error is not correlated with the actual explanatory variable. In this case, the measurement error must be correlated with the observed explanatory variable, and the OLS estimate must be inconsistent. The assumption that the measurement error is not correlated with the actual explanatory variable is called the classical errors in variables assumption, or briefly, the CEV assumption. Here is the derivation of the inconsistency in the OLS estimate. For a simple regression model, the probability limit of the OLS estimator beta 1 hat can be written as the population parameter beta 1 plus the ratio of the covariance between x1 and the composite error in the estimated model to the variance of x1. We write the covariance into two terms. The first term is 0 by assumption. For the second term, the covariance between x1 and E1 can be written as two terms. The first term equals 0 because of the classical errors in variables assumption. So the covariance equals minus beta 1 times the variance of the measurement error. The variance of x1 equals the sum of the variances of x1 star and the measurement error. The CEV assumption also makes the covariance between x1 star and E1 equal to 0. Therefore, we obtain the probability limit of the OLS estimator beta 1 hat, which equals the population parameter beta 1 times a component. That component is positive and less than 1. It implies that the OLS estimator beta 1 hat is biased toward 0. It is called the attenuation bias. If beta 1 is positive, then its OLS estimate will be downward biased. If beta 1 is negative, then its OLS estimate will be upward biased. The marginal effect of x1 on the outcome variable will be underestimated in both situations. From the inconsistency formula, we know that if the variation in the explanatory variable is large relative to the variation in the measurement error, then the component is close to 1. The OLS estimate will be close to the population parameter. The attenuation bias will be small. In a multiple regression model, the measurement error in an explanatory variable causes the attenuation bias for that variable. The inconsistency formula is parallel to that for a simple regression model. The variance of x1 star is replaced with the error variance in the auxiliary regression. We use the auxiliary regression to parcel out the effects of other explanatory variables. After ruling out the influence of other explanatory variables, the error variance is equivalent to the explanatory variable variance in the simple regression model. Measurement error in one explanatory variable also biases the OLS estimates of the other explanatory variables, but the direction and magnitude of the bias are uncertain. Today, we discuss the OLS estimates when the explanatory variable is mismeasured with error. It leads to an attenuation bias under the classical errors in variables assumption. The OLS estimate is biased toward 0, and the marginal effect of that variable will be underestimated. In other words, the estimated marginal effect is less than the actual marginal effect. Therefore, if we find a non-negligible marginal effect of an explanatory variable, the measurement error in that explanatory variable should not be a major concern because the actual marginal effect could be larger. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.